Hello, everyone. Let me check my microphone. There we go. Okay. Uh, 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 uh. Okay, there we go. Hello, everyone. Welcome to the stream. Coming through on a starry night, it's yours truly, the illustrious Phantom Thief. Here's Oshimoto. And it's homework time. I may have forgotten about my homework, so we're gonna do that today, because I forgot. There we go. Huh, okay. Hi, I have to lock in. So we're doing a study stream today, because I need to study. Let me just like... Go. Shift over a little bit. And actually, that's fine. Okay. Hi. I don't really know if anyone's... But if you want to study with me, you can. I'll make a quick comment. There we go. Yeah, we're just gonna study because I forgot about my homework. Okay, let's see here. How about... Here we go. So, I have homework due tomorrow. Like, some pretty big homework. And I totally forgot about it. So now I have to lock in. Like, I have really important homework due tomorrow, and I totally forgot. So we're just we're just gonna study here. Also, I just ran onto Dover Syndrome and found some nice BGM. This seems it's good for the soul. So, I've been like going back and forth on like what the message up top. No, I think I liked it better. There we go. I like it better like that, with that font. There we go. Okay. We'll go with that. Maybe you guys will find this relaxing. What I like to do when I study, I like to put on some rain sounds as well. So let me, or at least like some sort of water sounds. I think rain and river is really my favorite. Let's look up those. Here we go. Alright. Okay. I like rain sounds a lot. There we go. Okay. Now I have to lock in. I'll probably start with my... Oh, can you guys hear my microphone clicks? Or not my microphone, my keyboard clicks. Let's see. I guess you guys can. Alright, we'll consider it keyboard ASMR. Okay. Discord. Mute. We don't need Discord. We don't need Discord sounds. Okay. There we go. I'm probably gonna start with my not very important homework first, which is my physics homework, because it's kind of easy. It won't take that much brain power, so it'll help me lock in for the other ones. I also have a what? Okay. Yeah. I also have what is it? My brain isn't working. I forgot what I was gonna say. Never mind. Okay, well. Okay, so relativity of time intervals. I need my paper. And my pencil. Hello? Are we back? Hello? Hi? Uh-oh. Sorry about that. That's strange. Oh, give me a sec. The stream might disconnect again. Give me a sec. Okay, and we're back? We're back, okay. Sorry about that. Something weird just happened with my stuff. Stop it. Okay. It's okay. There we go. Okay. Okay. We're just gonna study for a little bit. The first thing I need to do is I'm gonna do is my physics homework. You guys can study along if you want. I'm gonna... Yeah. Sorry, I think the internet has been a little bit spotty as of today, so I hope stream doesn't disconnect and reconnect again. It doesn't keep disconnecting. I just kinda need to do my homework. Yeah, so that's what we're doing. Let's see. I need to think about this. Okay. So... Okay, so I have a particle. It's moving at 2.6 times 10 to the 8th seconds. And the average life in the laboratory is double that. So let's see. Okay, I need to time intervals. Okay, so where's my calculator? Use a TI-84. I like my TI-34 better for most calculations, but I'll use my TI-84. Let's see. Proper time between two events. Timer to... Okay, so... Clearly I've done this problem wrong. Still in the same events measured in the second frame reference. Proper time between two events. The Lorentz factor. So, time dilation. Question is, which one is the proper time? So, what if I flip this equation around? Have I done this wrong? No, but that doesn't work. It can't be 2. So, Huh. Is it really not that? I don't know what I feel like am I really doing this incorrectly? Alright. Okay. So let me look at this equation. So in time dilation, the okay, with time dilation, the equation is the and time in the second frame of reference is equal to the original frame of reference over 1. Am I algebra wrong? Okay. Alright. Hello, Frigoko, welcome. Good for you, I guess. Please just don't burn down my homework. Am I dumb? What? Okay. Alright. Measured at its average lifetime in laboratories is to be that. Here, I'll look up their video tutorial of how to do this. They have a video tutorial on how to do this homework. What am I doing wrong here? So I don't have that part of the equation though. So 1 I'm gonna take a shot in the dark. No, that wasn't it. Okay, let me rewrite this equation then. Okay. So it's the hi Pressview, welcome. Okay, so time dilation, it's the new time is equal to the new time is equal to the old time, the original time, divided by the Lorentz factor, or multiplied by the Lorentz factor, which is the original time over the square root of 1 minus the speed at which the object is moving relative to the first frame of reference over the speed of light. So delta TO. So okay. Oh yeah, we did hit 1K subs. Thank you. It was very exciting. I wonder if I can actually rate people. I actually haven't checked. Maybe I can. it might take a couple days to unlock. Or maybe I don't get it until I get monetized. Let me check right now, actually. Edit. Oh, we can redirect. Oh my gosh, we can finally, we can actually raid people now. Oh my gosh, that's so exciting. I finally have access. That's all I wanted, honestly. I don't care about anything else, any other features. I don't even care about getting monetized. It's the fact that we have access to actual raids now. Oh my god, that's so exciting. I don't have to do manual raids anymore. Okay. So that's okay. Yeah. So it's a rest frame. So okay. I don't know what the problem is. Wait a second. I think I'm dumb. Give me a okay. Oh my god, I figured it. I did it. I'm dumb. That's why. Okay. It's not because my math was wrong. Well, it is because my math was wrong. It's that I just missed a decimal point. Okay. So let's see. 4.20 times 10 to the negative 7th power seconds is equal to 2.60 times 10 to the negative 8th power seconds over the Lorentz factor, or whatever. 1 to the minus u squared c squared square root. So then 1 minus u squared over c squared, the square root of that is equal to 2.60 times 10 to the negative 8 seconds over 4.20 times 10 to the negative 7 seconds, which is equal to so 0.05. So then 1 minus u squared c squared is equal to math homework. I am currently doing physics homework. Yes, it is math. Yeah. Squared. Okay. I missed a decimal point. That's my issue. Okay, so that means u squared over c squared is equal to no. 1 minus 0.0025. Okay, so 0.9975. So then that means that u is equal to c and then the square root of 0.9975, which is equal to the square root of that is 0.99875 c. There we go. Okay. And all I did was miss a decimal point. 875. At 5? Submit. Eh? What did I screw up? This should be right. Isn't that my velocity? Talking about X and Y, why didn't we talk about you and I? Wait until you get into physics and then you start using the Greek alphabet. Sorry. For some reason, my cough has been, I don't know, my cough has been flaring up today for some reason. I'm not quite sure why. I apologize for coughing into the microphone. I'll try not to do that. What am I missing here? Okay. What is 2.6 times 10 to the negative 7th, no, negative 8th power divided by 4.2 times 10 to the negative 7th power? Am I missing something? Oh, I'm stupid. 4.6 to, 2.6 times 4 times 2 is 5.2, not 4.2. Okay. Okay, no. Yeah, I am just dumb. Okay. Man. 0.06 19045. Alright. Those are cool pickup lines, but please don't use them on me. I'm not. Please don't flirt with me. I'm not interested. You can save them for someone else. Okay. Okay. So that would be. Yeah. No, that's wrong. What's this squared? Squared is equal to 0.0038322. So then 1 minus our answer is 0.99617. 99617, which is then equal to I'll do 678. 678 instead of that, and then we'll do, okay, let's go to the square root. Okay, this should be correct now. 0.9961678 is equal to, which is equal to, okay, so the square root of that is 0.99808C. There we go. Okay. Is that correct? 99808C. And I thought this was gonna be easy. I mean, it was easy. I just did my math wrong. Why has this been so laggy? It's been laggy all day. I don't understand. Okay, I got it correct. Next one. What distance measured in the laboratory does the pion travel during its lifetime? Okay, so I mean its average lifetime. Okay. I hope this is what I think it is. Okay, so so what is that? 0.99808 C times, let's do 3 times 10 to the 8th power, store as my x value for this. This value times the time of its life, which is 2.6 times 10 to the negative 8 seconds is equal to, so what is that? 0.99808 x times 2.6 times 10 to the negative 8th power is 7.785. 7.785 meters. Is it the other one? Is it 4.2? Is it 100? Is it 1.25? Is it 125.76? Okay, got it. So I just had to do the other value. 4.2 times 10 to the negative 7 seconds. This is confusing. Wait, so, oh, it's because in the rest frame of reference. Okay, I understand now. Sorry, I had to cough. Okay. Let me see how many questions I have left on this one. I got 2 more questions, and then I think I'll move on to a different homework, which I probably should do. I forgot my homework. Okay, it's fine. Let's see. Muons are unstable subatomic particles that decay to electrons with a mean lifetime of 2.2 microseconds. They are produced when cosmic rays bombard the upper atmosphere about 10 kilometers above the Earth's surface, and they travel very close to the speed of light. The problem we want to address is why we see any of them at the Earth's surface. This is a very classic question. This is a very classic question. I can answer this. Alright, so let's see. What is the greatest distance a muon could travel during its 2.2 microsecond lifetime? They travel very close to the speed of light. Okay, well, it doesn't say. Okay, so what is 2.2 microsecond? Microsecond is, I think, 1/100,000th of a second? So what is that? 2.2 times 10 to the negative 6th power times the speed of light. 660 meters. Did I get it right? I think, yeah, I got it right. Okay. So, if they are produced 10 kilometers above the Earth's surface, but they can only travel 660 meters, which is 0.66. So it's only 0.66 kilometers. It's not even a full kilometer. Then how do we see any of them at Earth's surface is the question. Going to answer the previous part, it seems that muons never make it to the ground, but the 2.2 microsecond lifetime is measured in the frame of the muon. The muons are moving very fast at a speed of 99.9% of the speed of light. What is the mean lifetime of the muon as an observer on the rest of the Earth? So, or at rest on Earth. So, we simply do time dilation calculation. So, if it's 2.2 meters, so sorry, ugh. Okay, so time is equal to what is that? 1 minus 0.999, that over, or no, so that's 2.2 times 10 to the negative 6th power seconds is equal to, what is that? So 2.2 times 10 to the 6th power. Oh, nope. Divided by the square root of 1 minus 0.999. Equal to 0.12345 957 57. Nope. Seconds. Submit. No. Motion speed of light. 0.2. Okay, so did I just switch it around then? Did I forget to square something? I forgot to square it. Squared. Yeah, okay. 4921. There we go. I got it right now. Okay. How far would the muon travel in this time? So, traveling at 0.999 times the speed of light, times 4.9 times 10 to the negative 5th power. 14685 meters. Let me find muons and cosmic rays. I don't know. I'm gonna Google that. Muons, cosmic rays. Created by cosmic rays hitting the atmosphere. Yes, I guess? Because they're made by cosmic rays? What? That's in... Okay, whatever, sure. I got it right. In the front of the room, so how to make the ground was the theory of the 10 kilometers to travel by as measured by the muon. The 10 kilometers through the atmosphere. So that would be 10 kilometers times the Lorentz factor from earlier. Times 10 to the so it's 10 kilometers. So 1, 2, 3, 4 power. Four hundred 47.1 meters or kilometers. No, meters. Submit. Is the moon able to reach the ground? Yes. Alright. That was easy. Oh, that was one I had to write down. Oops. Okay, I have to write that one down. Let me go back and redo my and write down my calculations. Alright. So, what is that? 2.2 times 10 to the 6th power, or times 10 to the negative 6th power seconds times c is equal to 666 meters, or 660 meters. B. In its lifetime? So what is that? T is equal to 2.2 times 10 to the negative 6th power seconds over 1 minus 0.999 squared, which is equal to 4.9 times 10 to the negative 5th power seconds. C. Human travel in this time. Distance is equal to 4.9 times 10 to the negative 5th seconds over times 0.999c, which is equal to 15 kilometers. What is that? Okay. D. Yes. E. Okay. So then H is equal to what is that? What is that? 1,000. Oh, I guess I could just put 10 kilometers. 10 kilometers. 10 kilometers times square root of 1 minus 0.999 squared, which is then equal to 0.45 kilometers. F. Yes. Okay. And the last one, I don't need to write anything down. Alright. That might be helpful too. My ADHD brain is like thinking about, or I don't know why I had to preface with my ADHD brain. My brain is thinking about the homework I have coming up, and it's just like, no, I don't want to. Please don't make me. Okay. I just gotta lock in. Do you want to like... Okay. Alright, 2 atomic clocks are carefully synchronized. One remains in New York, and the other is loaded onto an airliner that travels at an average speed of 240 meters per second, and then returns to New York. When the plane returns, the elapsed time on the clock that stayed behind is 3 hours. Which reading with the clock the twos differ. So U is a binomial expansion? What? I'm not doing that. I don't feel like doing that. Okay. So, in Takahara and the rest frame of reference. So 3 divided by the square root of 1 minus, what is that? What is that? 240 divided by x squared. Ah, that's why. The difference is so small that my calculator does not want to do it. As a binomial expansion? What is a binomial expansion? Review. Okay. It's just relativity. Okay. I'm gonna figure this out. What is a binomial expansion? I probably know what that is, I just don't know the name of it. Okay, let's try this. 3 insert. So insert 3 times 3 hours times 60. That's minutes. No, times 60 times 60. It's still so tiny that it won't do it. That it won't show me. Okay, what is 240 divided by the speed of light? 8 e to the negative 7th power. So 1 minus answer. That okay. Maybe we go to Desmos scientific calculator. Okay. So what is 3 times minutes times seconds divided by the square root of 1 minus 0.1, 2, 3, 4, 5, 6, 7 squared. Squared. Oh no, that's not right. That's not correct. 0 point times 1, 2, 3, 4, 5, 6, 7. Come on, I want to show. You need to show me more. Scientific calculator. Scientific calculator. 100 decimal places. Full precision calculator. There we go. Okay. Okay. So what is... Okay. 3 times 60... Nope. 3 times 60 times 60 divided by 1 minus 0.1234567 squared to the power of 0.5. Okay. 3, 4, 5, 6. 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 point... Okay. Where is this? 3.456 times 10 to the negative 9th power seconds. Okay, I did it. It's correct. Which clock will show the shorter elapsed time? Shorter elapsed time. The one on the airliner. There, okay. That's physics done. Now I can go on to my other homework. I don't want to do it. Okay, it's fine. Let's lock in. Alright. I need to make a poster, so it's graphic design time. Oh god, I'm kicking myself. I should have done this earlier. I wish I did. I'm gonna go... Oh, I still have coffee left. Ooh. Okay. Coffee is tasty. Okay. Let's think. Think, Kurtis, think. Wait, I have a paper. Ooh. I have a paper with instructions. Let's see. Okay. I have to figure out how I'm gonna measure the sun. That's my project. And I have tomorrow to do it. Let me get a boo womp. We have one of those? Hold on. Is there a boo womp sound effect in this server? There we go. I wonder if I should take a mental break. Okay, let me read this to myself real quick. I have to like look up some stuff. I want to get like, you know what? While I'm trying to figure out what I'm doing, how are you guys doing? If anyone wants to, anyone like to chat? Hello, chat. How are you on this fine night? What are you guys doing? Hopefully you guys are responsible and not like me, forgetting to do my work. Okay, let's see. It's such a boring looking poster. Alright. Oh. Alright. I was looking at one of the example posters. It's so boring looking, but I guess that's what I'm gonna go with. Right. And oh, there's no better way to get started on a scientific paper than to look up other scientific papers to reference. What's it called? My brain wants to shut off. I don't want to do this, but I have to. No, that's not it. Ugh, it's almost. I didn't even look at the time. It's almost 1 a.m. I want to sleep, but I can't yet. Not yet. I must be strong. My homework, my grades. Okay. Let's look at these. Sun. The sun. Man, I wish I was paying attention in class. It's so hard to pay attention in class, though. I can't. I didn't post the slides either, so... Oh, oh, oh. I did post the slides. Yay. The corona. So I need to make like a to-do list for myself. Like really understand this. Open a new window. Okay. Okay. This one, new folder. Alright, and then we will new Google Doc to make my to do what I need. So what do I need to do? Imager, spectrometer, or particle detector? Big instrument. How dynamic? Wait. Okay. How should I do this? I think a spectrometer would be cool. Pick an instrument. So, spectrometers are cool, I think. Spectrometer. What are we using it for? What are we gonna use it for? I think it'd be cool to use a spectrometer to see if we can detect atmospheres. So that's what I'm gonna write my thing about. Is that basic? Is that too basic, actually? E measuring and why? Because when a thing, I like that idea. I like exoplanets. Okay, using it for to detect, to find elements. Something I'm comfortable with. To find element spectrometer to find elements within exoplanet atmospheres. What are we using? Yeah, that's what we're gonna use. I just remembered something. Okay, it's okay. It's fine. Yeah. So we're using it to find elements within the... Hello, Press Fail. Welcome. Yes, we did get a new model. Hi. Hello. I'm currently working on homework. Okay, so we're gonna use a spectrometer to use it to find the atmospheres. You got a source. Let's go find sources. Okay. Hello. Okay. Come on. Show me the papers. I need to go look up some... Okay. So here's what we got. I need to come up with a mission to use a spectrometer. Okay. So here's my idea, right? I'm supposed to make a presentation about, hey, you pick a scientific instrument, how you want to use that scientific instrument to do stuff. The idea that I decided I'm gonna go with just right now. I've decided right now that, so when like an exoplanet, like orbits in front of its star. I think, if I remember correctly, I think a little bit of, like, some of the light will come through the atmosphere, and we can detect that light, and we can detect what, like, wavelengths it is to determine what molecules or compounds, basically what elements are within that atmosphere. So I think I'm gonna write about that. Also, this is not working. Why is this not working? I just want to look up some papers, please. I just want to look up some scientific papers. Okay, well... What other sources can I go with? That's not working, clearly. This one? No, okay, let's go. Okay, let's try this. Spectroscopy exoplanet atmosphere. Let's see if that'll work. Technical description and performance of the Phase 2 version of Keck Imager and Characterizer. High-res spectroscopy, effects of mass planet uncertainties, effect of chromospheres, and coronae on exoplanet transmission spectroscopy. Sounds interesting. Alright, let's scroll through and see if this has the data that I need to figure stuff out. Exoplanet atmosphere detectants, enticing, like, that sounds like it'll be helpful. High temperature measurements of... This must be so boring. Now that I think about it, this is probably really boring to listen to. I'm listing off scientific papers. Like, scientific astronomy papers. Being like, oh yeah, no, we're gonna use spectroscopy to determine elements in exoplanet atmospheres. I mean, this is boring for me. I can't imagine how boring it is for people listening to this stream. Oh well. Don't focus on me. Focus on the rain noises and the music. Okay. Let's see. What else we got? This one looks like it could be good. Okay. Let's see. We've got the influence of stellar chromospheres and coronae on exoplanet transmission spectroscopy. I just said coronae out loud, and I was like, oh, like I thought my brain immediately went to dog. A main source of bias in transmission spectroscopy of exoplanet atmospheres is magnetic activity of the host star in the form of stellar spots, faculae, or flares. However, the fact that main sequence stars have a chromosphere and a corona, and that these optically thin layers are dominated by line emission may alter the global interpretation of the planetary spectrum, has largely been neglected. The fact that that's okay. I always hate weird long sentences like that. Using a JWST, James Webb Space Telescope, NIRISS/SOS dataset of hot Jupiter HAT P18b. What? We show that even at near IR and IR wavelengths, the presence of these layers leads to significant changes in the transmission spectrum of the planetary atmosphere. Accounting for these stellar outer layers thus improves the atmospheric fit of HAT P18b and increases its best fit atmospheric temperature from 536 Kelvin to 736 Kelvin, a value much closer to the predicted equilibrium temperature of about 852 Kelvin. Our analysis also decreases the best fit abundance of CO2 by almost an order of magnitude. The approach provides a new window into the properties of chromospheres / corona in stars other than our sun. That sounds promising. So this is detecting atmospheric temperature, and also it's detecting the abundance of CO2, which sounds like it could be useful. I'll have to scroll through this paper though. Witness of exoplanet atmospheric detections. Okay, let's read this abstract. The classical... Oh, God, how many pages? It's a 25-page paper. That's not that bad. Okay. This one even gives me a method as to how to... Oh, that's how to make... Okay, I need to find a paper that goes over the process of using a spectrometer. Spectrometer. So just spectrometer. Thermal emission toward exoplanet transit spectroscopy. This looks promising. Sulfur dioxide in the mid-infrared transmission spectrum of WASP-39b. That sounds like they went over that they detected a compound that they have a process for it. That could be very promising. Okay. Recipes for forming a carbon-rich giant planet. Okay. I mean, that's actually interesting, but unfortunately, I don't think that's going to be useful for my current position. Sections of an Earth-sized exoplanet orbiting near ultra star. Ooh, okay, that could be helpful too. Observations, yes, these are what I need. Okay. Methods to characterize exoplanet host stars in spectroscopy. Abstract. Exoplanets is a characterization of their host stars. One of the most powerful tools to characterize stellar properties like effective temperature, surface gravity, and metallicity. is spectroscopy. Oh yeah, by the way, I don't know if you guys have heard this. I think this is absolutely wild. As an astronomy student, I think this is wild. Apparently, any element that's heavier than helium, astronomers will call a metal, which means carbon, oxygen, nitrogen. Those are all metals. If you're ever reading a scientific paper about astronomy, that seems a bit wild to me. I don't know why those are metals. I mean, I get for the sake of like generalizing things. Most of the gases in that you're gonna be detecting if you're doing astronomy is gonna be hydrogen, helium. That's like the vast majority of it. So it's not too much of a stretch to lump all the other elements together as just metal. But I don't like that. I don't like the fact that, I don't know, it just doesn't sit right with me that anything that oxygen and carbon and nitrogen are all metals. In astronomy short speak. I don't know. That doesn't feel right to me. Okay. Okay, so this one looks like it's instead of determining stuff about exoplanets, it's more determining stuff about their host stars. So I don't need that one. The mid-infrared instrument, or the MIRI, medium resolution spectrometer, the MRS. The MIRI's MRS? Is that what this is saying? Mid-infrared instrument, the mid-infrared instrument medium resolution spectrometer. That is a mouthful of a name. Who decided on that? JWST has potentially important advantages for transit and eclipse spectroscopy of exoplanets, including lack of saturation for bright host stars, wavelength span to longward of 20 microns, and JWST's highest spectral resolving power. We here test the performance of the MRS for time series spectroscopy by observing the secondary eclipse of bright stellar eclipsing binary R Canis Majoris. My brain blanked out halfway through that sentence. MRS, right? Okay, this looks like they're detecting stars more than exoplanets. So described a method to detect carbon dioxide absorption in the nearby temperature exoplanet Proxima Centauri b. Okay, not completely useless. Okay. Sulfur dioxide in the mid-infrared transmission spectrum of WASP-39b. The recent inference of sulfur dioxide in the atmosphere of hot Saturn mass exoplanet suggests that photochemistry is a key process in the high-temperature exoplanet atmospheres. We observed this during this. Okay, using a resolving power, where this is the wavelength. Okay. Check the time series. We present the detection of an Earth-sized exoplanet. Oh my god, there's so many credits for this paper. Where's the abstract? Okay, at the bottom of the main sequence, ultra-cool dwarf stars are widespread across the neighborhood. The philosophy have left the planetary population are unexplored. TRAPPIST-1 has been found hosting a planetary system. Present the speculos. They definitely spent a long time making that acronym. The project's detection of an Earth-sized planet in a 17-hour orbit around a ultra-cool star. High radiation combined with infrared luminosity and Jupiter-like size. Detailed emission spectrometry characterization. Oh my gosh, wait. That sounds like it could be good. Hold on. Introduction. This, blah, 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 blah. It sounds like it could be good. Results. Geoastrophysical cases had to be excluded. It's constrained. Star's luminosity. Small size of the host star. Transiting planet. Planet is very small. Equilibrium. Mass since it's competition. We are that also affects rocky composition. The intense emission. The sustained silent. Discussion. Speculoos. We then modeled these emission spectra for several poly and baroque surfaces. Oh, okay. Oh my god, my brain is not liking this. Make it possible to measure day-side expression vector. Okay, shows how speculoos compares in terms of emission spectroscopy and transiting of the day mirrors of rock, and the potential of the planets where emission spectroscopy is quantified using this, which is separate observations. Not only reveal the could not only reveal, I don't know if this is actually gonna be helpful. Oh, it's so word dense. I don't want to look at this. Okay. I really don't want to look at this. This is so word dense. I don't like it. Okay. Plus one's a little bit easier to read. Transiting exoplanets, context. I'm really starting to kick myself now. I really should have done this earlier. Well, luckily I can just kind of BS my way through this, I think. As long as I know what I'm talking about, then I think I can do it. I'm gonna go get some water. I'll be right back. Okay. Transit, eclipse, and phase spectroscopy. Perfect. This is exactly what I needed. This paper is what I needed. Okay. Methods. Okay. Okay. The long-awaited James Webb Telescope launched on Christmas 2021. It's already been 2021? Wow. Or, I didn't realize the JWST has already been out for like 3 years. It's now started to provide its first observations in the infrared. Simulations. Okay, this simulation is cool. I want to look at observation though. Instrument setting. Simulations. Calibration. Tools. Adding photon noise. We perform simulations of each observed as part of this. Building the simulations. Data reduction and analysis. Oh, maybe this isn't what I need. It's all about. This is all about simulation. This isn't about actually using the instrument. This one looks pretty promising though. Transit observations have been detected at active regions on WASP-52. We present the first JWST observations of WASP-32b. Alright. Introduction. This is so... My brain can't read this. Oh my god, okay. Okay, I'm just gonna read this. Maybe I should just look up a paper instead of looking up papers about this. I should just look up something about how transmission spectroscopy works. That would probably be a lot more helpful. These papers could be useful. It's just that they don't tell me, they don't go over the process, which I mean, I guess makes sense. Transmission spectroscopy is such a like something that's it's something that people have known how to do for a long time. And maybe it's not worth making the paper over. Here, okay, this paper will probably tell me what I need to know. As planets orbit their stars, they pass from our point of view, starlight passes through the atmosphere, particles, but from that light, as absorption happens at specific wavelength of light. Setting which wavelength of starlight has absorbed, we can determine what kind of particles are present in the atmosphere. Okay, this is... I should have just done this before. Okay. Yeah. Okay. So I've got a spectrometer. Oh my god, okay. What exactly do I need? And the effects of CMEs. Mission is needed. Am I pitching a mission? Solar dynamic events. I might have been looking up the wrong thing the whole time. I don't know. I think I was looking up the wrong thing this whole time. Alright, I'm probably gonna end stream. I think I need to go get up, take a mental break, and now I'll get back to my homework. Okay. Bye bye. It's also getting late, so I'm gonna go take a break, and then I'll continue my own time. All right. I'll see you guys later. I'll try to go post my schedule soon. All right. Bye bye. See ya. Have a good night, everybody.